Good morning, everyone. So, Chana, let's start off. Yeah. So, the last thing that we did was this problem. A solid sphere of m and r suddenly shrinks, to half the radius. So, find the new omega. Let's see. Question on that. Something similar. Hope everyone revised the notes. It's a theoretical question. If all the ice at the poles melt, what happens to the duration of the day? Increase, decrease, remain same? Depends. Something. Get it? If all the ice at the poles melt, what will happen to the duration of the day? Answers, anyone? What happens to the moment of inertia?
Increases.
Moment of inertia increases. If you remember, we have done this thing before. Let's see. So all the ice is at the poles. So when this thing melts, the moment of inertia increases. Because the distance is more. Remember this question? We have done this before. We did this in moment of inertia. If ice at the poles melt, the water will be spreading over, so distance increases, the moment of inertia increases. Okay, we did this thing here. So since there's an external forces, L bar is constant. That is I omega is constant. So if I increases, omega decreases. What about the time period? Time period is 2 pi by omega, na? If omega decreases, time increases. The duration of the day increases. So one of the advantages of global warming, you get more time per day. Copy it, next thing. Now look at this thing, same thing. Suppose if you have a person in space holding some dumbbells kind of thing. Others, keep your cams on. Like that, gravity is in space. And is rotating with omega. Now if he brings the hands closer, what will happen to omega? If he brings his hands closer, what do you think will happen to the omega? So there are two questions. What happens to omega? You can say this is a question only. What happens to his kinetic energy? So he'll bring his hands like this, he'll become closer. Tell me what will happen to the omega and what will happen to the kinetic energy? Will the energy of the system increase, decrease, remain same? Answers? What will happen to I?
Decrease.
Jesus, no? I decreases. And if we know L bar is constant, there are no external forces on the system. So I omega is constant. So I decreased, so omega increased. Then what about the kinetic energy? Kinetic energy is what? Half I omega square multiply and divide by I. This becomes I omega whole square by 2I. That's nothing but L square by 2I. If you see, we have a quite a similar formula in this thing. Kinetic energy is momentum square by 2m. No? Remember this? So we get the same formula here, L square by 2I. But here L is constant. So kinetic energy is proportional to moment of inertia. So if I decreases, what will happen to kinetic energy? Increases. That is how you know. Because see, half I omega square mein, omega is increasing and I is decreasing. So that overall quantity is increasing. This is a better way to figure it out. So kinetic energy is L square by 2I. L is constant. If I decreases, kinetic energy increases.
Sir, we can also say that they both increase and decrease by the same amount, and the
Factor.
and omega is squared, so
You can say
it would
that.
increase.
Yeah, you can say that. But this thing gives you a better clarity. Na? You can see and say, ha, so and so. Karke. Clear? Next one. Tell me one thing. Let's say we have a person standing in space with a umbrella kind of thing. Now, if he starts rotating the umbrella, what will happen to the man? Any idea? You're just standing in gravity-free space. You rotate the umbrella clockwise. What will happen to you?
You will rotate anti-clockwise.
Yeah. So, Dhruv, come on, Jia, Soham. So what happens here? So torque external is 0. That means L initial is equal to L final, but L initial is 0 because it's at rest now. Therefore, L final is also 0. So what should happen here? So for the L final to be 0, the man and the umbrella will rotate in opposite directions. Just like, linear momentum. If I throw something in the forward direction, I'll go backward direction. In real life, you don't see this thing because of air resistance and friction. But if you do this actually in the space, this thing actually happens. So if this guy rotates this way, this guy will rotate this way. So if you say this is clockwise, this will be anti-clockwise. I think during 90s, right? 94, 92, these people launched a satellite to Mars. Jupiter, actually. The name is also Levi Shoemaker, I guess, something like that. So what happened, during that time, 1980s, these old cassettes, they used to have magnetic tapes. So this is a reel. Na? You have seen this kind of cassettes. So they rotate there. So when they launched the satellite, right, and when they started the recording, the wheels will rotate here. Now to compensate for this, the whole satellite started rotating in the opposite direction. And then on Earth, you never encounter such kind of problems. In space, you start seeing this kind of stuff. Put it up. I'll show you something. Clear. Next thing.
Hi, my name is Mike Foster.
You can hear the audio?
Expedition 29. Welcome to the
Yeah, he's talking also very lightly, but you can hear some kind of sound, right?
Why the International Space Station doesn't tumble in its orbit
Nothing?
around the Earth. Well, we have a system.
Check na free. I think you have a problem. Others are saying they can hear.
System, if you will. There's really two ways to
Anyway, we're not interested in what he's speaking right now. I'll just show you. He's in the International Space Station.
Will continue to rotate around
this is the guy in the problem we did with space.
Acted on by an external to the product of its rotational inertia.
Watch carefully what he's going to do. Explain them.
The rotational inertia.
And he's talking very slowly.
And angular speed. How fast is it moving? The angular momentum and rotational inertia, that includes the mass, are constants in the system. Angular momentum of the system remains constant if no external force is acting on the system. This is the law of conservation of angular momentum. I can demonstrate this to you with me actually doing a little bit of a demonstration here. So I want you to watch this. I'm going to have to unclip the microphone or I'll tie myself up in knots.
Let me show you that again.
Again,
what he's doing? He's stretching his hands and he rotates. Now, when the hands come closer, what will happen? I will become less. So his rotation speed will increase. If he puts the hands away, I increases. Again, omega decreases. Then he puts the hands again inside and then he becomes straight. So see. He's rotating, I is decreased. I increased. I decreased, he became straight. I decreased even more.
Again, what's going on as
Did you see the last way? He rotated much faster. Now see, he'll rotate more faster. So you're getting what is happening there? So I into omega is constant there. Let me show you one more.
This is a norm, and then have my and then see how close I got.
See.
You can see my tie flying up. So ice skaters use this principle.
You see, when he brings the dumbbells closer, this omega increases.
You can see my tie flying up. So
The thing
ice
is that,
skaters.
this angular momentum looks quite weird actually, because when I say I omega is constant, you all are like, oh, okay, sir is telling the fine. But it actually happens. Getting it? And these things, that angular momentum in physics is really one of the tough concepts to visualize. People say it is more difficult than quantum mechanics because it looks totally counterintuitive, like, okay, what is happening there? Let me show you this. This is a cool one. This is a good video. I'll post this in the group. And I feel like, I should buy that thing as a turntable. This kid is playing here. The teacher is like, stop playing. Wait, we have to do the experiment. This is the problem. So when the dumbbells are away, I into omega, I is more. When you keep the dumbbells close, I is less, omega is more. I1, I A omega is IB omega. This is that umbrella problem. Huh? See what she did. Just see everything. I'll show it again. Let's see that again. Now see what she did. She took a tire ka wheel, initially at rest. Now she'll rotate the wheel. Now when you rotate the wheel, angular momentum will be there. To conserve, she will rotate in the opposite direction. Fair enough. Then what she did, now once it rotates, now see, initially it was rotating this way. So she was rotating the opposite. Then what she did after some time, she will reverse this wheel downward. Then what will happen to conserve angular momentum? She'll rotate in the other direction. Now clearly see. She's rotating towards you now. Suddenly she will rotate away from you. Now she's going away from you, coming towards you. Now she will rotate the wheel. Okay. Can you see her rotation reversed? Because when you reverse the wheel, angular momentum of the wheel reverse, so her rotation also will reverse in order to conserve the angular momentum. This is the umbrella problem. Getting it? Make sense? So this thing actually happens. And not only this thing, suppose if you have a helicopter. Now this helicopter has these blades, no? If you see, if these blades rotate this way, to counteract this thing, the helicopter will rotate in the opposite direction. Devin, cam on. Ardi, Jia, Kanan, Priya, Soham, cams on, everyone. Don't sleep. I know I'm showing you videos, and don't bring popcorn, Pepsi, and start eating. These are educational videos. You're not having fun. You can have fun, nothing wrong, but see. So if you see the helicopter rotate in the opposite direction, so to counter this thing, what do we do? How do you think you'll stop the helicopter from rotating it? You have one more fan here. Must have seen the back tail mein. So this thing generates a force in order to stop it from rotating. That means, in order to shoot down an helicopter, what you need to do, if you can just shoot the tail, the helicopter will automatically rotate and crash. You must have seen in movies. The soldiers are going in an helicopter and the tail gets hit or something and the helicopter rotates round and falls. Ever seen that? This is an old video of some actual thing. The tail got damaged. The moment the tail, for some reason, it had an accident, it fell off, the helicopter started rotating. Because the rotors are rotating in one direction, to counteract, the helicopter rotates in the opposite direction. Normally, that rotor ka tail is actually just keeping it in equilibrium. Got this? So the tail is the weakest spot of an helicopter.
Sir, but the momentum isn't conserved, right?
Where?
In the
Angular
helicopter.
momentum.
Yes.
This guy is cancelling out that momentum, no? Whatever
But
you're rotating
MG is
here,
acting as an
but
external.
that will pass through the center only, no? So we are rotating about the center of mass only. You take torque about center of mass. The mg won't matter. You always take torque about center of mass. See, even when it rotates about the center of mass. Okay. So there. So that is how you can shoot down an helicopter, by hitting the tail. So tail is a weak spot. So the tail gets damaged for whatever reason, you need to put the helicopter down. You can't fly it. Even you're there or sleeping. Why do we need to keep it tail 10 times, right, everyone? I don't get it. Keep it on, huh? Now I think I have to do small research on, people who keep the cams off and the results, and maybe put the presentation tomorrow in the group. You have a PTM, na? Next thing. And not only this thing, if you see, there are certain weird, very difficult to explain few things like this thing. See, this is that angular momentum based on ice skating.
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
By using angular momentum. There. And some training. Someone took a video from the Winter Olympics and made an angular momentum video. But you can actually see that girl rotates quite fast. And that is the main principle, angular momentum. So now if you see, right, you can't explain this normally, like, okay, why it is increasing. We say angular momentum, but looks kind of weird, but works. If you see certain things like this thing's anti-gravity. This guy, Vegetarian, right? He has a YouTube channel, pretty popular guy. It does very good experiments, right? You should definitely visit when you are bored or have nothing to do, right?
Here at the University of Sydney, where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a...
It's called a flywheel. What's a flywheel? Flywheel is nothing but a rod with a disc. The disc can rotate. You're getting that? That's called a flywheel. A disc which can rotate and attach to a rod.
Meter-long shaft.
He's explaining well, so let's listen then. I want
to trying to hold this out horizontally with just one hand at this end.
The audio is clear, right? Yeah.
It is virtually, it is impossible, okay? Now I'm gonna let go. You gonna be able to hold this at all?
I hope so.
Can you lift it out? Make it horizontal, hold it, hold it, hold it. Come on, just try to, I want you to hold it out horizontal. See if you can. Hold it, hold it. Oh, come on. No. What I'm going to do is I'm going to spin this up to a few thousand.
So basically he proved it is very difficult to lift it. Getting it is 20 kg, catching at the end and lifting is not that easy, even for that bodybuilder guy.
RPM. And then I'm going to attempt just that, to hold it from one end and have it out horizontally. Five, four, three, two, one. Boom. I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal.
There.
You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go. I mean, it's just kind of awkward with the hand.
Careful.
There.
Woo! Just barely. Oh goodness, do you even lift?
So there's almost 20 kgs of weight. He's struggling to lift.
Clearly, I do not.
That too, where did he catch? He caught at the point where there's more weight. Huh?
Daunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Go! That was perfect. Now I'm going to release my left hand and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1.
Can you see what he's doing? Initially, he was struggling to lift, by catching the heavier end. Now he's catching the end and like we say, that the beam ka gada types. So if you see, right, this is how you can do magic tricks. Imagine you make a contraption like this, you something like this only, the gada types, right? And inside there's a wheel and a motor. You can't see this thing. So you'll tell someone from the audience to come and say, try to lift it. He will try to lift, he can't lift. But when you lift it, there's a small switch here. You press it on, the motor starts rotating and then you start rotating it. You switch it off and say, it is not fake. Come on, you try it again. and the other guy can't lift it again. So if you see, right, this is what happens when you take science to the extreme. It looks like magic. And this concept is actually pretty difficult to explain what is happening, but I'll try. It's like, what is happening here is this weight mg is acting here, and this guy is going in a circle. So if you see, mg is always down. And if you look at the angular momentum, L bar, it is away from the center. Can you see both are perpendicular? So the torque created by this will be like this. The torque is this, mg is this, and L bar is this. All three are mutually perpendicular. Just think of it like this, okay? If you apply force, should the speed increase? Yes or no? No. In a circular motion, when velocity is this way, force is perpendicular, na? Speed is constant. Isn't it? In a circular motion, even when you apply force, speed is constant, velocity is changing. Meaning you're using all the force to change the direction, but not the magnitude. Make sense? So something similar is happening here. The mg is used to rotate the vector ka direction instead of changing the vector. So there is a weird explanation, gyroscopic precision karke. So we don't have in the portion. And this is the reason I was saying, there are certain phenomena you can't explain that easily. Mathematically, I can explain, but still it will feel a little vague. But that is how you make an anti-gravity wheel. Fair enough? Did you ever see a top? The top spins like this, na? But it doesn't fall down, isn't it? That is because of the same reason. Top also does a gyroscopic precision. Okay, let's see one more. So we have a disk rotating with omega, mr disk. Someone took another identical disk, is placed on it. It will become like this. Find omega final. So you took another identical disk and kept on top of this thing, so omega will change. So what is that omega final? Just give it a try. I'll be back in a minute. Answers? Any answers? See now. On the system, torque external is 0. So L initial is equal to L final. What is initial? Disk I omega. What is final? I plus I omega final, na? That's it. So omega final is omega by 2. So speed became half. Make sense? Put it down. Clear? Next one. Same question. We have a disk rotating with omega, mass m and r. Another disk of same thickness and material. Same material and thickness. But half the radius. Meaning like this, you kept it. So this is r by 2 and this is r. And this is omega final. Find omega final. Only difference between this and the previous is the disk is half the radius. Answers?
16 by 17 W.
Yeah. Others? See. So for this, the volume is how much? Pi r square into thickness. This is mass m. This is r by 2. And what will be this volume then? Pi r square by 4 into thickness. That means this mass will be m by 4, no? What is this moment of inertia? Mr square by 2. What is this moment of inertia? M by 4, radius by 2, by 2. Mr square by 32. Since torque external is equal to 0, L initial is equal to L final, you get I omega for R. This is IR, this is IR by 2. Will be IR plus IR by 2 omega final. This would be mr square by 2 omega, mr square by 2 plus mr square by 32. So omega final would be mr square will cancel 2 to 16. You get omega is 17 by 16 omega final. Omega final is 16 by 17 omega. Take it out. Any step you didn't get, please ask me. Here. Next thing. So if you see this thing, so that's a disk, okay? He's rotating with the hand. And on the computer, right, you can, he's connected a device there. So it will plot omega versus time. He keeps a disk. You can see it slows down. See, omega suddenly dropped. Let's see it again. He rotates the disk with the hand, it's spinning. So omega is decreasing slowly because friction is there. But when he keeps the mass, suddenly omega drops. You can see it slows down. And look at the graph, omega suddenly drops. Like this. So I1 omega 1, right, is equal to I2 omega 2. So the total angular momentum on the other side, total moment of inertia. Look at this thing. When the car goes in one direction, right, the wheel goes in the other direction. So if the man is jumping in the forward, the plank comes backward. See. So kind of makes sense. Whatever direction you're going, it is pushing the plank in the opposite direction. So it rotates in the other direction. Look at this thing. He took a mass, he threw it onto this thing. He must have done this in the park, right? The merry-go-round is there, you run fast and jump on it. It rotates. Kind of like that only. So the man comes and jumps onto the plank. The angular momentum is conserved about the center. So it rotates. That's our next question. Top view. Mass M, radius R, it is hinged. So we have a bullet here of mass M going with speed U. Hits here and sticks. Bullet of mass M and speed U hits the disc tangentially and sticks. And basically gets stuck. Find omega. So after getting stuck, what happens? This bullet is stuck like this inside, and this whole setup is rotating with omega. Just the problem which I showed you right now. Instead of a bullet, he threw a mass which went and got stuck on the table. So find omega after it gets stuck. What do you get? show you. See. Initially, when the bullet is coming here, mass m, speed u, you're taking torque about the hinge. So what is the system here? System is bullet plus disc. So what is the perpendicular distance? This. Since torque external is 0, L bar is conserved. Therefore, L initial 0, the disk is not moving only. Plus your bullet would be MUR K cap. This is your bullet. It's like a particle. Hope everyone remembers how to calculate. Then when this thing gets stuck, and this whole setup is rotating with omega, the bullet is also stuck. So V bullet will be how much? R omega. We always keep the bullet and the disc separately. So bullet is rotating, going with the R omega speed. So L final would be disc will be how much? I omega K cap. That is for the disc. For a bullet is a particle. So M V bullet into perpendicular distance K cap. So if you substitute here, I end up with mr square by 2 omega plus m into r square omega. L initial is equal to L final. Equate them. MUR is mr square by 2 omega plus small mr square omega. You get omega would be mu by mr by 2 plus mr. That's your answer. Check it out. Have a look at this. Any step you didn't get, please ask me. Clear? Any doubts? On the page? Put it on, put it on. Let's see, next one. This was asked on G. Same problem, and now we do it in the reverse. We have a disk. There's a man standing here. Man jumps tangentially with you relative to the platform, meaning with respect to the platform, will jump with you. Then what happens? The platform will go back, the man will jump front. So find omega. This is a top view. Hope you got it. Like you are standing on the merry-go-round on the edge and you jump on tangentially. So the merry-go-round will start rotating. Find omega after he jumps.
So do we need the mass of the man in this question?
Yeah, small m. Show you.
So is it 2u by 3r?
Masses are not same, right?
Oh, sorry.
Capital M, small m. See, listen carefully, and this was also asked in the JEE exam. Initially, when the man was standing here, everything was at rest. So L initial would be 0. Now, when the man is jumping, you need to understand something. The point where he is jumping, this is going with omega. This point here goes back with r omega. So the point where the man stands moves backward with r omega. Getting it? And how is the man jumping? The man jumps u forward. So what will be the velocity? U minus r omega, na? You're getting, we did this in the Planck problems also. When the man is about to jump, the Planck starts going back. So he's actually not jumping with u, he's jumping with u minus v there. So here he jumps with u minus r forward. So back with r omega, and man jumps with u forward. So actually he's jumping with u minus r omega in the ground frame. So what is L final? I omega plus k cap plus mass of the man, speed is u minus r omega, perpendicular distance r minus k cap. So this is the perpendicular distance. And we know L initial is equal to L final. L initial is 0. I is mr square by 2 omega minus m into u minus r omega into r. When r goes out, you end up with mu by mr by 2 plus mr. If you see, you get the same answer as this. So if the bullet hits tangentially or the man jumps tangentially, you're going to get the same answer. Put it on. The most common mistake what people do now, they think man is jumping with you and that's all the problem. Man is jumping with respect to the platform with you. So meaning in the ground frame, he actually jumps with u minus r omega. That was the main thing. Put it on. Ask me if there's any doubt on that. Clear. Next thing. Spinning bullets. You know, normally whenever you fire a gun, the bullet actually just doesn't come out. It actually comes out spinning. So if you ever see a, you know, the gun ka barrel, this is how the gun ka barrel looks actually. It's not a smooth tube or something. It actually has a grooves inside. So when the bullet comes out, it doesn't come out straight. It comes out rotating. Now, why did they do this thing? If you see now, during 1700s, when the guns was first invented, they're pretty inaccurate actually. You know, they used to have a range of like what, 10 feet or 15 feet. And after that, the bullets used to become very inaccurate. So if you see how the wars are fought also, you will think it is quite funny. There's a scene from one of the movie. This is the American War of Independence. So that is the context here. This is how armies used to fight. Because the guns range is very short, you have to come very close to fight. And how the people fight. The other people are still walking. It is literally madness actually. Now look at the other guys. Now their problem is what? They're just waiting to get in the proper range. They know the bullets don't hit properly, so they're just walking straight into the other guys. And see.
This battle was over before.
So it was kind of deadly. Yeah. Now, if you saw the ball, how did it came? The ball just went straight. Yeah. But if you see actually the guns how they fired, look at this thing.
Hello, the internet. I'm Gav.
I'm Dan.
We're the Slow-Mo Guys, and today we're in Bama.
Roll Tide.
Indeed. We don't really do gun videos very often on this channel, do
Yeah,
we?
tend not to. Last time we were here, and we had an M4 on fully automatic.
Very scary.
Yeah.
We've also been known to use a dweeby little air pistol, but today we're massively stepping it up a notch.
By approximately 1 notch.
I can't even fit in the frame
It's
with
too,
it.
yeah, see you later. Destin from Smart Every Days lent us this beefcake of a 50 cal.
Thanks, Destin.
Big gun, huh?
Again.
It's going to blow you away.
Looks like some animated thing, right? But if you see in US, right, you can buy any type of gun, any number of guns you want. In India, it is illegal. You want to buy a gun, you have to apply for a license. They will then do a proper investigation that you need a gun, and they'll give you some dabba pistol of 6 bullets. You won't get guns like this and all. But in US, right, you can stockpile this kind of gun. This is a 50 caliber gun. Normally, these kind of guns are used to shoot armored vehicles and tanks. Getting it? So, that's the one good thing. Imagine you are allowed to buy these kind of guns in US. What happens? You know, the teacher is teaching angular momentum. The student gets pissed off. Next day, he'll bring a gun and shoot everyone in the class. Right? That's what normally happens abroad. So India at least teachers are saved because you don't buy guns.
Want me to fire it?
Oh, you're going to be... You're right there, breathe.
Terrified.
It is. Yeah.
Why'd you have this?
That's it.
Oh!
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 Yeah. So profesh.
Or the trigger.
Moved before the gun and it like shook your face.
Oh God! Oh my
me.
face!
I love it. Like the air
You can see the
moved
recoil.
before the gun and it like shook your face and then the gun shakes you afterwards.
Incredible amount of force.
Not too bad.
The bullet when it goes out, right, it pushes there so fast you get a shockwave.
I'll tell you, that is tooth shattering.
Yeah.
You can see the shockwave visibly go from the end of the weapon there, follows all the way down the gun into me, and then I react.
You can see there's a
Sack of
recoil.
meat.
Like a
and
very
bone.
violent Newton's cradle.
Yeah.
If you see, it is 28,000 frames per second, meaning you slowed down the camera by 1 by 28,000 times, and you still can't see the bullet. The bullet is going so fast, getting it? It is almost traveling at a speed of 3 to 4 kilometers per second. 3 to 4 kilometers per second, meaning Ghatkopar to Mulund, you will go in what? 3 seconds or 4 seconds? So that is the kind of speed we are talking about. They'll slow it down more. 1,30,000 times. Now you can see the bullet spinning. See the bullet spinning.
Water we can...
10.
And look at the fire graphic, huh? It looks like a graphics only. That fire is still there.
Lovely stuff.
If you see that bullet is spinning almost like 60-70,000 RPM. High omega. So now why spinning helps you? Because see, imagine you have a bullet, right? You must have played with a fidget spinner, right? When you're playing with that spinner, did you ever try to rotate it? You have to apply some force to rotate it. It is not that easy. So when the bullet is spinning here, you get an angular momentum like this L bar because of the spin. Now, if the bullet becomes like this, or if the bullet becomes like this, if the bullet deviates, and this is the issue. If for bullet to deviate, L bar should change. Or let's write like that on. If bullet deviates, L bar changes. And if L bar changes, implies there is an external torque. Therefore, there should be an external torque. But we don't see any torque. But we don't see any external torque. If you're taking torque about center of mass, so mg ka torque won't matter. The air resistance will apply a little torque, but it is not much. So therefore, there is no deviation, or there is a very less deviation. So this doesn't happen. So it's like if you have a bullet which is spinning, it goes like a proper parabola. That's why if you see sniper rifles, they have long barrels. Because longer the barrel, more you can spin, more accurate you will be. But if you have a bullet without a spin, it will go up to some extent. Then you're gone. You don't know how it will go. It could go in any way. The path becomes random. So whenever you're firing guns, right, ideally speaking, the spin should be there. That's what made guns more accurate and more powerful. Clear? Put it up.